Once it was well understood that the air around us contains matter, and that this matter does exert pressure on its surroundings, we wanted to be able to measure this pressure. One way that was devised specifically to do this is called a barometer. A barometer is a glass tube that is closed at one end and then filled with a liquid like mercury that is chosen specifically because it is non-volatile, which means it does not evaporate. It will remain a liquid. The tube is then inverted and placed into a container of that liquid. The atmosphere exerts pressure on the liquid, which keeps the liquid in the tube at a particular height. So by observing the height of the column of the liquid in the tube, we can see how much the atmosphere is pushing down on the liquid, and we are thus measuring atmospheric pressure. If we were to use water, normal atmospheric pressure can support a column of water over 10 meters tall, which is not terribly convenient for storing or taking measurements. So we decided to use a different liquid. Mercury is much more dense than water, so a mercury barometer will not have to be so tall. In fact, atmospheric pressure will support a column of mercury that is less than 800 millimeters tall. And this relationship between the height of a column of mercury in a barometer and atmospheric pressure is where we get the conversion between atmospheres and millimeters of mercury. The pressure exerted by a fluid due to gravity is called hydrostatic pressure, which is represented by P, and is equal to the height of the fluid times the density of the fluid times g, the acceleration due to gravity. We can see that this equation will accurately predict the atmospheric pressure necessary to support a column of mercury of a particular height, if we plug in some known values. For example, let's examine the idea that a height of 760 millimeters of mercury is equivalent to atmospheric pressure, if the density of mercury is 13.6 grams per centimeter cubed, and the acceleration due to gravity on Earth is 9.81 meters per second squared. We will want all our units to agree, so we can plug in the height of the column and convert to meters, the density converting to kilograms per cubic meter, and then the gravitational acceleration. We will get about 101,000 pascals, which is equal to atmospheric pressure, and therefore corroborates our experimental observation.